Ledvina, and I would like to tell you something about Quasar Accretion-Disc structure and Microlensing-Induced changes in iron K alpha line. So in the first part, I'm going to tell you something about gravitational lensing and especially about gravitational microlensing. In the second part, I will show you some observational data from Chandra, and in the third part, I will show you our model for modeling the iron line, modeling for the caustic crossing of accretion disk. So here is the image which was the astronomic image of the sun last week. Here you can see the Lensing galaxy and the 4 macro images from the Quasar QSO 2237, and it's famous because its name is Einstein cross. So now we continue to some theory. We assume that here is some observer, here is the galaxy plane, it's our lens, and here is the quasar plane, it's the source of our light. The photons which are emitted from the quasar is deflected in the galaxy plane on a gravitational field of whole galaxy, and then we can observe multiple images because there are not only one extreme away from the some point on quasar to the observer. For the deflection angle, we are using a first post-Newtonian approximation of general relativity, so the deflection angle depends on theta, which is the observing angle by this equation. For a continuous matter, the equation is very same because we are only integrate through all sources in galaxy plane. Here is the surface density in the galaxy plane. Now we can write a lens equation in this simple way, but we have to scale the alpha by this factor, but I haven't said it yet. These distances ds, dds and dd are the angular distances. So if we would like to find the distance between this origin and the origin of the galaxy and the point where we are looking to the star, we simply multiply the angle by the angular distance. The second variable, the second thing which is very good to define is critical density. It's defined by this fraction, and it's famous because the galaxy surface density must be greater than this critical density to observe multiple macro images. Also, we can define a convergence, which is only scaling of the surface density of the Lensing galaxy. The application I will show you after a few slides. And last thing which is good to define is Einstein radius of the star or of the galaxy, and this angular distance sets us the typical scale in our systems. Now I have got here one more image of our observer, which is Chandra. Here we have got a source, and the light from the source is deflected on the gravitational field of Lensing galaxy. So we think that we are observing 4 sources, A, B, C, and D. But it can happen that, for example, the image E, we are observing in the part of the galaxy where is star population. So these photons can be additionally deflected on the gravitational field on each of the star in galaxy. This generates also multiple images, but its separation is about 1 micro arc second, so we can't observe the additional images for image A, but we can see the higher flux from A image in compared to B, C, and D images. So here are the examples of amplification maps. The galaxy in its plane generates this amplification map in a source plane of the quasar. So if we are moving with a quasar through its plane, on this map are shown the observed flux. The observed flux. So if we put the quasar, for example, to this point, the observed flux will be approximately 10 times larger than if the quasar lies somewhere here. In these three images, we are increasing the convergence of the stars in galaxy. So we are increasing the surface density of the stars. In this simulation, are neglected the continuous matter in the galaxy and also the shear. But it's not a problem because both of them are only changing a little bit a shape of this caustic network, or changing the average amplification. So it's not the problem. And in the rest part, we are going to talk about single crossing this caustic, for example. So it's we don't need to know what structure have got a caustic network around. Here is written the equation how to calculate observed flux. This I observe is the specific intensity of the source. This is an amplification factor, and we are simply integrating through some accretion-disc or something like that. On the amplification maps, you can see two main types of the caustic. One is the fold, and the second one is the cusp. There are also some another shapes, but these two are most common. But in the rest of talk, we are going to study only the fold caustic, because it is much easier to approximate that by some analytical function, and there is only one parameter which characterizes this fold caustic. So now I will continue to the second part of the talk. This is the observational data from Chandra. It was published by Chartas et al. In 2012. They are looking to the quasar RXH 1131 1231. On the top sketch, you can see the ratio of the flux between the image D and C, and flux ratios between image D and B. Here you can see that the flux ratio is first increasing and then decreasing in the time. So, but because of its flux ratio, it's the significance of gravitational microlensing, because this might be caused by intrinsic variability, but if it is intrinsic variability, we have to see the changes in flux in all of the images, not only in the one. Here you can see that the changes only in the image D. And on the right image is shown the spectral changes during this period 1, period 2, and period 3. On the top image, there is a spectra of the image C, and you can see that during these 3 periods, the spectra is approximately the same. But on the bottom image, you can see that during period 1, which is the blue spectra, you can see here one peak. During period 2, which is marked by red line, you can see here 2 peaks on another energies, and during a third period, there's once more approximately nothing, which looks like the same as the image C. I haven't said it yet, but this peaks is it's caused by lensing of iron line, because it's at the energy, is in rest frame energy about 6.4 kiloelectron volts. Now I continue to introduce our caustic model, and on the next slide I will introduce our disk model. We are approximating fold caustic by this equation. Here for the y equals to 0, the amplification factor diverges. It's because at line x equals to 0 is caustic. Outside the caustic is the amplification factor constant, and it's equal a 0, and inside the caustic we have to add to this background amplification the factor 1 square root of 1 divided by y tilde, and y tilde is our coordinate system which is connected to the caustic, and y0 is the caustic strength. Now I would like to tell you something about our disk model. This model was provided to us by Lukáš from Astronomical Institute. We assume that in the center there is a black hole with a spin A, and around we have got a geometrically thin disk. The emission, we assume that the emission of the disk have two parts. One part is the continuum radiation. There is some normalization constant. There is a dependence on emitted energy. It has got a slope gamma, and here there is a dependence on Boyer-Lindquist radius. It has got a slope q. Then we assume that the disk emits the emission from the iron line. Here we also here is also the some normalization constant, also the dependence on Boyer-Lindquist radius with the same slope q, and the shape of the line is delta function. But if the photon is emitted from the disk, it's deflected by the gravitational field of the black hole, so the energy, observation energy of the photon is another than the energy of the photon which is emitted from the disk, and the ratio is a G factor. Then we assume that the path from the disk to the observer it's not a straight, but the photon is deflected by gravitational field, by gravitational field, and alpha beta are coordinate system outside of the Kerr metric, and beta is parallel to projected spin. This transformation was calculated by Lukáš, and it was published in 2004. Here you can see the transformation equation between the emitted specific intensity and observed specific intensity for continual radiation and for iron line radiation. We also cut the disk at ISCO, and then we are cutting the disk at 99% of total flux, but this external cut is only because of changing, because of saving computational time. Now I show you the animation, what is the changes in spectra during caustic crossing the disk. Sorry. On the left image here you can see our linear model of caustic. This is a disk with inclination of 70 degrees, spin parameter is 1. Then we assume that the continuum spectral index is 2 and the radial index is 3. These curves which are plotted here are contours of G factor, and the thick lines correspond to the integer values of observed energy of iron line, and this white line corresponds to the G factor equal to the 1. So this is the contour when the iron line, observed energy of iron line will be 7 kV, here will be 8 kV, here will be 5 kV, and so on. And on the right part of the image you can see the raw spectra, it's the bottom one, and the lens spectra, which is the upper one. When the caustic is far away from the center, you can see that the lens spectra and the raw spectra looks approximately the same, but after a few seconds, for example now, here you can see that the shape of the lens spectra is, there is a huge difference between a lens spectra and raw spectra, and there is a spectral feature, this edge, and we would like to prove that this edge is here because the caustic is is externally tangent to this G-factor contour of the 7.5 kiloelectron volts. Now I can play the movie now, and here you can see a peak on the spectra at 8 kiloelectron volts, and we think that this peak is here because of the caustic is internally tangent to this G-factor contour. And we think that this peak have the same origin as the peak which are observed by Chartas. And after the few seconds, for example, now you can see that the lens spectra looks approximately the same as the raw spectra, but it's multiplied by the constant, and it's caused by inside the caustic there is the higher amplification factor than outside, and but inside is approximately constant amplification factor. So the next slide. Here is the one snapshot of the video, and now I'm going to tell you something about the spectra and its components. The first component is the continuum part. It's caused by the continuum radiation from the disk, and the second part is the radiation from iron line. But we can split the radiation of iron line into two parts. First is the blue smooth part, and then the pink peaky part. And we think that the origin of the peak is only this small area around the tangent point of the G-factor contour, and where the G-factor contour is tangent to the caustic. And I would like to prove it in next few slides, but first I have to introduce you to our coordinate system. So here is the same image of the accretion disk. Here are the coordinate alpha and beta. Here is the central black hole. Then you can here you can see the caustic which is coming to the central part. Here is the coordinate system x tilde and y tilde, which is connected with the caustic, and in this coordinate system we have written the amplification factor, and then here is the coordinate system x and y, which we are defined that both of them have got the same origin, but the coordinate system x and y is parallel to the G-factor contour, so the x-axis is parallel to G-factor contour. And here we are going to simulate a spectral shape of the small circular area which was shown few slides before. Here is that circular area. By the lines this line shows us the contours of G-factor, and by this line is the caustic, and this shadow strip, which I hope you see, it shows us what is the internal part of the caustic. What's the internal part of the caustic? As it was shown in video, we need some curvature in G-factor contours. So the simplest model which is able to provide us a curved contour is this Taylor expansion. So we will use it. So I forgot, sorry. And in the bottom part is the corresponding spectra to this situation. On the first two sketches, you can see that if the caustic is internally tangent to the G-factor contours, then the peak is generated. And on the last one, you can see that when the caustic is externally tangent to the G-factor contours, then the edge, we can see the contribution to the spectra from this small area like an edge. On the sketches between them, you can see approximately nothing, especially on the first and the fifth. But on the second and third, you can also see the peak, but the peak is generated by the caustic, which is tangent to some contours, but not here in the origin, but somewhere outside of the origin. So that's the reason why we see here a peak, but here the peak is misaligned from the but the peak is misaligned from the center of the area. So the main result is that caustic must be tangent to the G-factor contour for observing peak or edge in the spectra. We also calculate asymptotic expansion of the flux contribution from this small area for the internally and externally tangent case. For the internally tangent case, the spectral shape is the logarithm of energy minus the observed energy at the origin of the circle. It depends on the specific intensity at the tangent point. So it will be very good for directly measuring the specific intensity in some point of accretion-disc. For when the caustic is externally tangent, the leading terms is the Heaviside step function. And on the last slide, I'm going to talk about this geometrical factor without the specific intensity factor. Oh, okay. So here is shown the map of the geometric factor square root of 2 divided by the derivative of the G factor in perpendicular direction to the caustic, and divided by the second derivative of G factor in parallel direction to the caustic. And was it shown on this image? For example, if we choose this point, that means that if the caustic crossing this point and its orientation is tangent to the contours of G factor, and also the orientation of the caustic is like that this contour lies inside the caustic. This map shows us the strength of the peak which will be generated on the spectra. So here we see here that the amplification factor is about 12, and we have to multiply this factor by a specific intensity in that point, and then we will obtain the caustic strength of which we are going to see on the spectra. There are also some strange curves when our approximation doesn't work, and because of that, here this geometric factor diverges, because on this point is the maximum value of G factor on the disk. So the first derivative vanishes. Okay. And on this curve, it's a points where are inflection point on there are inflection point on G factor contours, so it vanishes the second G derivative in direction parallel to the contours. Yeah. So thank you.